different video, different perspective of the material that we're learning in this course. After looking under the hood and taking a peek at what happened when you call functions in the C programming language, now we're going to go back at 20,000 miles high view, and we're going to talk about something that is a lot more conceptual, something that has a lot more to do with the design of computing solutions, the design of algorithms, the design of programs to solve specific problems. We are going to talk about recursion. So first, I should preface this by saying that recursion is a topic that you're going to revisit throughout your entire curriculum. So we are just trying to do a quick introduction here. We are touching the tip of the iceberg, okay? But as you get used to the concept of recursion, as you revisit it in different courses, in different scenarios, etc., you are going to progressively get familiar enough with it that you can integrate it in your toolkit to solve problems. And this is really where you're going to see it pay off its dividends, okay? So, with this little preface out of the way, what is recursion? That's one way to look at recursion. Okay, recursion is when a function, a recursive function, I should say, a recursive function is a function that actually, inside of its code, calls itself. So this is a scenario we have never encountered before, okay? And you probably didn't encounter it in your introduction to programming. If you did, then congratulations, you have a heads up here. But most introduction to programming, very first programming classes, skip a little bit that topic. We talk about how we call functions. We talk maybe about how coding function works actually, and we talk about the stack and stuff like that. But we don't necessarily talk about the scenario in where one function is calling itself. That may sound silly at first, at first consideration, to say that a function could call itself. What if I call a function to do a job, and as a response, it calls itself and saying, well, I'm going to do the job. Yes, and this call is going to resolve into what? Well, this call is going to resolve into the function calling itself again. I'm going to do the job. And the function calling itself is going to resolve into the function calling itself and saying, I'm going to do the job, and so on and so forth. So this is really easy to fall into like infinite recursive patterns that make no sense, actually, that are not really useful, okay? If you want an example, a humoristic example of this kind of pattern, here's the index of the C programming language by Kennigan and Ritchie. The index for recursion lists all the pages where recursion is actually defined or used in an example or something like that. And of course, the last entry in that index is the page of the index itself. Okay, so let's try to go toward a somewhat more useful definition of recursion. And we're going to start defining recursion without actually talking about programming per se. We're going to talk about something that all of us are familiar with, a to-do list. If I ask you to define a to-do list, you could come up with many different ways, I'm sure, to explain to somebody else what a to-do list is. Well, I'm going to suggest to you one way. I'm going to tell you that a to-do list is either an empty list, so there's nothing to do. Okay, so here's my to-do list, it's empty, I'm done for the weekend. Or a to-do list is one thing, one task that I have to do, so the description of the task that has to be done, immediately followed by a to-do list. What does that look like? Well, it's actually what we call a recursive definition, okay? And it's telling us pretty much that this here, an empty list, would be a to-do list. But if we want to look at it in more detail, one description of one task to do, followed by a to-do list, would be also a to-do list. So we have two possibilities, right? We have two possibilities for defining the to-do list. And I'm going to put a sign here to mention that this is completely empty, okay? So what does that mean in practice? That means that if I have a list of one task, two tasks, 3, 4 tasks, okay? I can actually, and I'm going to number them quick, 3, 4. I can actually map this definition to this actual to-do list, right? This to-do list here, after all, is just the task number 1, followed by the definition of a to-do list. Okay. This definition of a to-do list can be, again, a task followed by a definition of a to-do list. So this is task number 2, followed by the definition of a to-do list. And definition of a to-do list, right? It's a task followed by the definition of a to-do list. See where this is going, right? Which is itself a task followed by the definition of a to-do list. Sorry about that, I cannot draw straight lines apparently. And then the definition of a to-do list can be there's nothing left to do. And there we go. You can see that you don't need to actually do computer programming to use a recursive definition. So the same way a recursive definition is a definition that uses itself pretty much in order to define something. It tells us in this case that a to-do list is an item followed by a to-do list or is nothing left to do. Okay? That's our definition. Well, in the definition itself, I'm using the concept of to-do list. I say a to-do list is one task plus a to-do list following it after a while. Okay? So that makes a recursive definition. The same way in programming, a recursive function is a function inside which the code calls the function itself. Okay? Let me show you a very silly example of this. Okay? We're going to look at a function that calls itself, and this one is going to be an infinitely recursive function, so it's not going to be a useful function, but we're going to call it do something. Okay? And the function do something is going to call itself. So maybe it's going to display something like printf, I am working on it, and then call do something. And I need a little prototype here real quick. Void something. Here we are. So let's compile this. So this is a recursive definition, right? Here's the definition of how you do something. You printf, I'm working on it, and you call the function do something. So you call the function do something, what is it going to do? It's going to display I'm working on it, and it's going to call itself, and so on and so forth. What happens when I run this? Well, what happens is there's a lot of calls going on, right? It's an infinite recursion. In fact, theoretically, it should be an infinite recursion because the function never completes. It starts doing the work, like I call do something from the main. Do something starts doing its work here, and then it says, okay, I have one more thing to do before I can complete. It's getting do something to complete. So we call do something, which starts displaying something on the screen again, and says, okay, I have one more thing to do before I can call it quit. It's call and wait for do something to complete. So we have all those calls to the function do something that are each waiting for the next one to complete. This is an interesting scenario that's different from where I call a function, like for example, function 1, I call it here, and then I say function 1, I call it again, and let's say that function 1 does something very silly, like for example, another printf. There we go. Doesn't matter what does function do, okay? We're learning what it is and what it means to call recursively this function. So this is function 1 speaking, okay? And I need a little prototype before the main. All right, so let's compile this and let's see what it does and compare, right? I'm going to comment out this line. Up. Compile, run, function 1 speaking, function 1 is speaking. So I call function 1 does something, then we reach the end of function 1, we return to the caller, the main. We call again function 1, it does something again. And then we reach the end of function 1, we return back to the caller, and we are here in the main, and we display main function is done, and we complete our execution. So this is very different from what happened here, where I called do something, and do something did something, but then the second task that do something was going to achieve never got completed because it was another call to do something, which did a printf, that part worked, and then it never completed and returned because its second task was to call do something, which did a printf, and then you get it, okay? So this is how we got our recursive infinity pretty much. But it's not really infinite, is it? When I was talking, I ran that program in the background, and after a while, segmentation failed, core dumped. So what's happening here? Well, what's happening is that every time I call a function, well, you tell me what's happening every time I call a function. It's awkward to make a pause like that in the video. It doesn't work quite well. So I'm going to move on. Forget about this. I'm not going to ask questions anymore. But my point is, try to remember last video. What did we talk about in last video? We talked about activation records, right? So every time I call a function, I enter a function, there is an activation record for that function call that is put on the stack, and it contains, all of the variables and parameters for that function. It contains the return address for that function call, and then when we are done executing that function, then it's over, it's removed. Well, so that means what? That means that if we're looking at our first example where I call function 1 and function 2, right? What's going to happen? Here's the bottom of my stack, okay? This is a main activation record, a stack frame, okay? And then I'm calling function 1. I'm going to push on top of the stack an activation record for function 1, which I'm going to abbreviate fn1. When function 1 reaches completion and terminates, this activation record goes away. Then when I call on line 10 function 1 for the second time, another activation record is put on the stack for function 1 again. When function 1 completes, that activation record goes off the stack. And when the main complete, this activation record goes off the stack as well. That's what we have been using until now, pretty much in programming. But when you look at do something, it's a little different what happens. Let's trace what happens, okay? So I start with, so this is going to be my stack. Oops. I start with the main function call activation record at the bottom, okay? And then I'm going to execute line 12, which is calling do something. You call do something, okay? So here's an activation record for that call to the method do something, okay? And I'm going to write here that this is the first time I call the method do something. So here's the activation record, including the return address and stuff like that. The return address says you were called from line 12 in the main. Well, it doesn't say lines, it says memory address, but you get my point. You were called from here, line 12 in the main. When you're done executing, come back and go through to the next instruction on line 13. The problem is, as we execute do something, we execute a printf, and then we call again do something. So we call again do something, here we are. We enter again the same method, do something, but a different time. And I call do something here for the second time. And the return address here, told me to go back to the main. Okay, and more specifically, it was line 13. Okay, go back to the main, line 13. When I call do something from inside do something, I make the call on line 19. The return address tells me, well, when you're done, go back to line 19. Okay? And then what do? I execute again do something. So again, an activation record for the method do something. That's number 3. All right. And this time the return address is, well, when you're done, go back to line 19 inside do something, because this is where you have been called again from, okay? So imagine that the code, and don't imagine, it is actually in memory in what we call the text segment, the text area of the process address space before. But the code is in memory somewhere, and you are executing instruction per instruction the code, and sometimes you jump to the list of instructions for a function, and you remember that you need to come back here, but in that function, you jump back at the beginning of the function, and you remember that when you're done, you should go back here first, finish the function, then go back to the main. So yeah, this is what's interesting about recursion. It's actually conceptually interesting, conceptually rich, okay? But we are still looking just as a very, very silly example. We are going to see much more useful examples of recursion than this, okay? But right now, just to let you know, this is what's happening here when I run this in the background. I keep coding recursively do something. I keep putting new activation record on the stack, but the stack is not infinite, okay? The stack is bound by the memory available, the memory that the process has available to do its job, and at some point, we are not going to have any more room left to put one more activation record. Bingo. This is what's going to happen here, okay? So we have been wasting a lot of memory here. We have been wasting a lot of memory putting all those activation records for that infinite function. So that's the first thing to understand about recursion, is the concept itself. Now we're going to look at more practical things, more practical examples. So I'm going to clean up my code a little bit here. I don't need function one. Actually, I don't need function one or do something anymore. We are going to call them, we're going to call our next function something completely different. Okay. My next function is going to be based on the fact that what does recursion seem to do? What do you think it's doing right now compared to what you learned already how to do before? Okay, you learned in programming, you learned how to do conditionals. Okay, test a condition, and whether the condition is true or false, execute this or that block of code. Then continue with the next instruction after the conditional statement. You learn to do what? Repetitions, loops, iterative statements. Okay, all of this is synonymous. So where you would say, here's a block of code and I want you to execute it and execute it again and execute it again and keep executing it again while a certain condition is still true. So you've done repetition, you've done conditionals, right? What does this seem like? Repetition, right? It is actually a way to execute again the body of a function over and over and over again. But the part that we haven't seen yet is, where is my condition? My condition to decide if I continue doing this or even if I stop doing this, right? So this is what we're going to look at now that we're going to investigate a little bit more realistic example of recursion, not something that just goes infinitely. But, we can make infinite recursions just the same way that we can make infinite loops. The fact that we can write infinite loops, that there can be sometimes infinite loops that are written by mistakes, etc., doesn't mean that we should totally stop using loops in programming, right? The same goes with recursion. So let's say that I want to do a countdown loop. So I'm going to start with a for loop. Since I'm telling you that recursion and loops, have like so much in common, let's start by writing a little loop here. So I'm going to write, let's use a while loop actually. Int counter equal 5, while counter greater or greater than 0, dot greater equal. I'm going to decrement counter, and I'm going to display puts, and I'm going to display a message. Actually, let's do a printf so that I can put the number easily. Printf the number followed by dot dot dot, or like something even better. Here we go. T minus the number, and then dot dot dot, and then backslash it. And I'm going to display counter. So this is a countdown, right? And then what happens when we reach 0? Printf, of course, ignition. All right. Let's give a little bit of a space opera theme to this silly little example. All right, so we are counting down 5, 4, 3, 2, 1, ignition. Okay, let's make sure that this is working. So I think I already saved it. Let's go back here, compile, run it. T-5, T-4, T-3, T-2, T-1, ignition, and main function is done. So I'm going to add like a backslash n here to space things out a bit. No pun intended, but that's it. Okay, we're done here. All right. So now what I want to do is I want to do this, but I want to do this repetition, right? This iteration things in a recursive style. So I'm going to call this void iterative countdown. I'm going to make a little function, iterative countdown, and that function is going to contain this code. I'm separating it in a function so that we can have a version that is iterative and a version that's going to be recursive. So iterative countdown, I didn't change anything, right? So if I compile again, run it again, there we go, it's still the same functionality, okay? But now what I would like to do is I would like to write recursive countdown. So I'm going to start the same way, okay? I'm going to put that here, and I'm going to put here, up, a cut and paste real quick. So that's code reuse, right? Not retyping the full name of the new function. That's either excellent code reuse or laziness, I'm not sure. I have kind of have an idea, but anyway. Recursive countdown, here's the code. All right. So how am I going to solve this problem recursively? So I want to replace by loop by a recursive function, okay? So that recursive function, I should be able to call it like, say, for example, countdown 5, and it's going to do a countdown 5, 4, 3, 2, 1 display on the screen, and then ignition. Okay. So I could have called, by the way, countdown 5 from the main directly. I put it in recursive countdown so that I can here very easily say, hey, I want to run the version of my code that's recursive, or I want to run the version of the same, the code that solves the same problem, but the version that is iterative instead, okay? So the fact that we encapsulate here things in a recursive countdown function, the recursive countdown function itself is not going to be recursive. This is just a place in the code where I'm going to play with my really recursive function. So countdown is going to be my really recursive function. I call it and I give it a parameter and I give it 5. That means I need you to count down from 5 down to 0. Okay? So let's write this function. Void countdown int. I'm going to call it just C. So what happens when we do a countdown? Well, when we do a countdown, we have to consider two cases, okay? We have to consider the case where we reach 0. So this is going to be called in recursion the base case or the stop case, okay? If C equal 0, then if C equal 0, I know what to do. I know that I should display on the screen ignition, blah, 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 \n, and I'm done. That's it. That's all the countdown recursive function has to do. If you call countdown and you say countdown 0, okay, this is the only thing you should be doing. You should be displaying printf ignition, and then you are done. Well, let's try it out. Let's try to just call countdown 0 and see if it's working. So compile. It's complaining about some stuff. Implicit declaration of function countdown. Okay, so I need a prototype, not an interesting error here. I'm going to fix it real quick. That's the prototype here, put a semicolon. Again, you don't need the name of the parameter in the prototype, but I'm going to leave it for this time. Let's try to compile again. Oops, I ran the previous version instead of compiling the new version. There we go. Now, if I run it again, so I'm using both functions. So let me comment out iterative countdown because we know that one works, okay? Let's see what the recursive countdown is doing for us. Ignition. Well, yeah, it's because I called countdown 0, right? Okay. So what happens now? What if I call countdown with 1? Well, C is not going to be equal to 0, so I don't know how to finish the job. I don't know how to display ignition, but I know that I have a countdown of 1. So what I should be doing is printf t minus %d, and then the dot backslash, and this is going to be my parameter C. So if you give me a value that is not 0, like 1, for example, I'm going to say t minus 1, dot, 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 and then I need to resume the countdown. I need to continue the countdown. It's kind of like I need to continue my iteration with a loop, right? Well, here I need to continue my iteration with a recursive function. So I'm going to call countdown, and this is a super important part. The parameter for that new call to countdown is going to be C minus 1. And that makes all the difference. That makes all the difference between the previous example, where we have this crazy recursive function that never stops, and a useful recursive function here, where in the case where C is not 0, so I'm going to put that in else, okay, I printf something, and then I call myself with countdown C minus 1. So the idea is that if C equal 1, right, so C is not equal to 0, I go to the else, I display t minus 1, dot, 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 and then I call countdown with 1 minus 1, which is going to be equal to 0. So I call again the function countdown, but now the parameter is different. The parameter is 0. And what happens when I run the countdown function with parameter 0? The if C equals 0 on line 21 is true, I display ignition, and I finish, I complete. So I return to whoever called me, which was an instance of the countdown function here. It reaches the end, it finishes as well, and so on and so forth. So now we can scale it up. Let's take a look real quick on paper, just to see it, to visually look at what it's going to be like. And I'm just going to do like the list of function calls, okay? Actually, no, I'm going to do the full stack trace. So, okay, here's my stack, as usual. So the main activation record is here. Main activation record. All right. So in the main, I call recursive countdown. So recursive countdown, like I said, is not our recursive function. It's just the part of the code where I'm going to play with my recursive function itself. So count down, sorry about the awful handwriting as usual. Recursive countdown, when it executes, is going to call countdown with 1. So this is the activation record for the call to countdown, the countdown function, which received parameter 1. When I call countdown parameter 1, this code is going to execute, right? So this is the countdown 1 activation record. Because C is equal to 1, I'm going to display something on the screen. Then I'm going to call countdown C minus 1, C being 1, okay? C minus 1 is 0. So this is going to call the method countdown again. Countdown again. But this time it takes parameter 0. And this method countdown with parameter 0 is going to execute and do if C equals 0, that's true, display something on the screen, and complete. And when it completes, the activation record goes off the stack. We are back where we called it, which was right here in this code on line 24, okay? We are back to line 24 where we did a call to countdown C minus 1 where C was 1, okay? that returned, we displayed something on the screen. We reach now line 25, the end of the if else, line 26, the end of the countdown function, and therefore we return to whoever called us, which was line 17. Inside recursive countdown, we called countdown with parameter 1. And since this was the only thing that we had to do in that function, now it's done, we return, we are back in the main, and when the main is done, finally, everything is cleared from memory. Okay, so we did it with the value 1, but what would happen if I put the value 2 here? Well, let's add a little bit of code here. There we go. I'm going to do what is called sometimes instrumenting the code, okay? I'm going to make the code display messages on the screen that are going to help us understand what it's doing right now. So every time I enter the function countdown, I'm going to printf countdown called with c equal, and I want the value of c. So every time I enter the function countdown, it's going to say, hey, the function countdown was called with this parameter value. All right. So let's take a look again. Start with 0. And we're going to run that. And the advantage of instrumenting is that it kind of allows us to do a quick trace, on the screen. So countdown call with c equals 0. That results in displaying ignition, and then main function is done. Okay. I'm going to say countdown between parentheses the value that was passed, okay? Starting. And then I'm going to display at the end countdown blah 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 complete. All right. Let's compile this. Let's run it. So I call countdown from line 17. Okay, I enter the countdown function. It says countdown has been called and is starting with parameter 0. Displays ignition. Countdown with parameter 0 is now complete. We will go back to the main. So I'm going to leave that on the screen, and we're going to compare it to what happened when I put a 1 here. So I'm going to have to recompile, execute. Countdown with parameter 1 has been called. It displays t-1. Notice that countdown with parameter 1 has not completed yet. Okay, we are here. We displayed line 24 t-1. Okay, and now we are calling countdown with parameter c-1. C is currently 1. 1 minus 1 is 0. So countdown with parameter 0 is starting. That one displays ignition and completes immediately. When it completes, we go back to the call to countdown index 1, which has nothing left to do, and completes like it says here on the screen. And if I keep going like that, you're going to see that it's always the same pattern. So I need to clear my screen now. It's going to be a little bit more printout. So countdown parameter 2 is called t-2. It calls countdown parameter 1, which displays t-1. And now countdown parameter 1 is calling countdown parameter 0, which is starting, displaying ignition, complete, returns. The countdown parameter 1 has nothing else to do, returns. The countdown parameter 2 has nothing else to do, return. And we're back inside the main. So it's very important that you spend the time to actually play with this and understand how this very simple recursive function that is just a replacement for a loop pretty much, okay, is working. Trace it, okay, do a trace on paper, do the stack diagram like I did, take the time to do it yourself so that you are sure that you understand, and then you're going to be able to find more examples, like namely the factorials, the Fibonacci. So the examples are going to become more and more, how to say, realistic. Okay, like the countdown is the simplest example I could come up with, to explain recursion. But now that you have this base ID, even if it's still a little bit fuzzy in your mind, right, blurry, keep at it. Look at the other example. Keep incrementally looking at examples that are more and more complex. And as usual, you know where to find us. Come to office hours, okay? Ask us plenty of questions. Use Piazza forums, whatever we're using this semester in the course, to also discuss this topic with your classmates and the TAs and myself, and we'll be glad to help you understand this concept of recursion. It's a very, very important concept in computing. So I hope that this gentle introduction has been opening your mind to this new way of solving computing programs. We are going to keep reusing it, and we are going to show you progressively as we go through examples that are more and more complex that recursion is actually, it requires an initial effort on your part to understand it, but it pays off a lot when you apply this technique, this technique for designing programs, when you apply it to either data structures or problems that are themselves recursive in nature, okay? What happens is that it's a perfect match. If you try to write a loop to solve a problem that is recursive in nature, you'll be able to do it, okay? Everything you can do with loops, you can do with recursion and vice versa. However, your program is going to be a little bit more awkward, maybe a little bit more complicated. If you have a problem that is recursive in nature, or a data structure that you manipulate that is recursive in nature, then you are going to see that applying a recursive solution, a recursive program design to that kind of problem or data structure is going to immediately match with the problem and give you a much better experience. Okay, but again, don't take my words for that. As you progress through the curriculum and you reach the data structure class, you're going to see all of this much clearer, much more clearly. Our goal right now is just to introduce the base ideas and have you practice with them so that you have a better time when you have to tackle more complex problems. All right, as usual, thank you for your attention.